Welcome to the class on VLSI systems design. A group of us has been working in this area for a couple of years now, but it's clear that it's a rapidly expanding area and one that we thought that is going to be extremely important to PARC. And so as that became more and more obvious, it became more and more, and I thought that we at least try to spread that knowledge a little bit further than our own group. And that was really the basic reason for starting this class. When I sent out the message asking for who would be interested in such a class, I was expecting a large response, but I wasn't expecting quite so large a response. By the time all the votes were in, there were at least 80 people who had responded, and a large fraction of those withstood the threats of hard work and projects and all that to indicate they're still interested in the class, and those are the approximately 50 people which are here today. And so I hope you all really will take this class seriously, and we honestly do expect homework, and we'd be extremely interested that everybody participate in doing some sort of project after the class to actually make use of the information that we've tried to disseminate during the class. One of the most exciting things about the response was that we've got somebody from every lab at PARC represented in the class, as well as from a couple of the subsidiaries, Shugart and Versatech. And so the interest really is as wide-ranging as we anticipated. And I think the bringing together of people of such a diverse backgrounds is going to be a challenge to keep everybody interested in the class in the various aspects, and B, tremendously exciting for the people in it, because they'll have a chance to talk and interact with people who are experts in other areas other than their own. And in fact, I don't claim to be an expert in all areas of the field either, and I'll probably be asking some of the people in the audience to answer some of the questions which are brought up, because there are specialists in the audience which I think are much more capable of answering some of them than I will be. This is not just a class in another new technology to design in. We're really talking about a whole new field of endeavor, a whole new field of research for computer scientists, for computer systems architects, and it's just really an exciting, sort of vibrant thing that's building up. I'm sure you're all aware of the excitement and competition and developments which have taken place in the IC technology half of the business in the last 10 years or so. The innumerable companies out in Silicon Valley are madly trying to produce chips of larger size with greater circuit density, and it seems like every week you open up a new publication and you're amazed at what the next chip is. And I can see the same sort of excitement and interest in competition and so forth developing in this new field of systems design. It's gotten to the point where the technologists have been working so hard and have progressed so far that they're starting to outrun our ability to effectively design in the medium in which they're presenting to us. And so that's what this class is all about, is trying to bring those people who are most intimately involved with design into contact with the integrated circuit technology and industry and design techniques so that they can exercise their design skills in this new area. The sort of people that are getting involved in this are as wide-ranging as you might expect. There have been, over the last year, there have been courses in the topic springing up at CMU, Berkeley, Caltech, UCLA, and various other universities. Lynn Conway just returned from MIT, where she taught a class last semester, and found just an extreme interest in all areas of the school in this sort of technology. She had people from the device physics side of things, as well as people from the computer science AI sides of things. And so there, as here, the range of people that are interested in this topic is really quite remarkable. The universities, however, are not the only places where it's beginning to become active. Lynn just mentioned to me yesterday or a couple of days ago, that DEC, Hewlett-Packard, Intel, those places are running courses similar to the one which we're starting here today, because the people in those organizations are beginning to realize just how important it is for these people of diverse backgrounds to work together to make best use of the technology. And that really brings up the question is what can PARC contribute to this area, and why is PARC in a unique position to make a contribution in the field of VLSI systems design? To understand that, let's just look at some of the areas of expertise which are required to effectively work in this area. And they include digital systems architecture, software systems architecture, and in software systems I don't just mean applications programs and writing programs to use the machines that the integrated circuit people design, but actually software people who are working with the designers to develop new languages to help better manipulate and help design, in fact, the circuits of interest. Then we need to also have a widespread knowledge among the systems architects, both software and hardware, the device physics people, and so forth. We need to have a widespread knowledge of the integrated systems design skills. We need everybody to have a baseline understanding of what the basic design techniques are, what factors are important in the design, what factors are not important, so that people can focus best on the problems which are most significant. And to really make the thing a reality, you need some responsive fabrication facility in order to fabricate the circuits which you design. If you intend to go around the loop of design and test and so forth several times, it's much more fruitful if you can have a design or a fabrication turnaround time of a week or 2 weeks or 3 weeks rather than 4 weeks, 5 weeks, 6 weeks, or 10 weeks. And unfortunately, the longer times have been the rule of the industry rather than the exception. And so fast turnaround or responsive fabrication facilities, especially in a prototyping environment such as PARC, where we want to design a lot of trial systems, maybe throw some away, go through iterations more times than you might expect in a production environment, that turnaround time for the fabrication is extremely important. And so looking at these areas and saying, well, where does PARC have expertise and versus other companies that may be operating in the field? We see that the PARC has very great expertise in both the digital systems architecture and the software systems architecture sides of the things. We're beginning to develop an automated fabrication facility, and the only thing that's been lacking so far up till now is a widespread appreciation for what the integrated circuit design skills are. And that's where this class fits in. We only want to supplement the capabilities that already exist at PARC with the sort of the last key element that will allow a wide variety of people to operate in this arena. Just in comparing where other companies are in this, you might expect that places like DEC or Hewlett-Packard might also have similar type of skills, although I think we would say that we have an advantage there. But a place like Intel may have they have good fabrication facilities, and they have not necessarily a widespread knowledge of integrated systems design. They have some systems architects, although they're really scrambling to establish a better foothold in both the hardware and software architecture sides of things. And really they had skills sort of down here and are just really scrambling to develop these higher level skills, which are so important for making use of the circuit densities which are coming in the very near future. The reason why we feel it's so important to be active in this area is due to some reasons which are shown on this slide here, some of which you may be aware of, but this is not just waving hands. This is almost certainly going to come to pass in the next decade. We've seen a vast improvement in the density of circuits over the last 10 to 15 years, and those who are acquainted with the technology and so forth indicate that there's no real good reason why we can't keep that advance going for another 10 years at least. And those advances most importantly involve the scaling down of the size of the circuits, namely geometries which are, for instance, 5 microns today will in the future be able to be made with dimensions on the order of 0.5 micron. which translates, since those are linear dimensions, that translates into a circuit area improvement of 100 to 1. So things which take up a whole chip now could take up, would only take up 1/100th of a chip in about a decade from now. But then you add to that the fact that we'll be able to double, at least double or perhaps triple the linear size of the chips, and you come up with another factor of 5 to 10 improvement in area capability. And the sum total is that what now fits on a chip, you'll be able to put 500 of those approximately on a chip in a decade. And when you realize that today's single chips are things like processors and so forth, you wind up with a mind-boggling possibility of 500 16-bit processors on a chip. And if that's what you want to build. And the question is, well, does 500 16-bit processors make any sense? Or are there much more interesting structures that we can build that make use of all that circuit density? And then you realize, well, gee, it takes a couple of years to design one of those processors today, and if you make this whole thing sort of equally random, the time to design will rapidly go out of sight. And so we need some much better, more regular structures and so forth for designing to allow us even to design, let alone make use of the densities that we're talking about in the future. All that does not come free, however. There's a whole set of problems, some of which I'm sure you're all familiar with. These can be considered awful problems or areas for research. I think we should look at them in the latter vein, that there's just a tremendous opportunity for research and innovation and interesting activity in this new field. And I've just started to list a couple of the things. There are obviously opportunities for, well, number one, we have the complexity problem, which is the one I just alluded to, of how you make use of millions of transistors on a single chip and how you design them. Complexity is nothing new to hardware and software people, but you're going to have it in spades in this technology. The new hardware will need new hardware and software architectures. That all has to be developed to make use of the technology. Some of those architectures may involve concurrency, problems of designing and representing algorithms which find and make use of concurrency, perhaps, if you have multiple processors in a system. How do you make them all work together and communicate properly and so forth? And in the more of the gleam of the eye category, there might be a possibility for establishing a better or more physical basis for some of the algorithms and ideas in computer science, because if you think about it, you've got this little tiny chip that's about a ½ inch on a side, and you're pouring all the energies of computer scientists and physicists and device architects into that ½ inch piece of silicon. And it's going to require a working together and an understanding of the other person's trade much more thoroughly than we've had to face in the past, I think. As far as the relationship or what kind of problems the integrated circuit industry provides for the computer scientists, there was an article in the September '77 issue of Scientific American, which was a special issue devoted to microelectronics. The reprint of one of the articles has been handed out as one of the notes, written by Carver Mead and Ivan Sutherland at Caltech, to give you some glimmer of the changes in computer science which might take place as a result of the evolution of integrated circuitry. Okay, so that's just a rough introduction to the area that we're going to be talking about for the next 5 days, the kinds of promise and problems that it holds. And one of the things I want to emphasize, that I want this group to really be the participants in this new revolution. And the way to do that is to start this week and actually start working the problems, working the homework, thinking about projects that would be of interest to you, and actually going out and designing something using the integrated circuit technology which is available to us today. And to make the designs worthwhile, or that design effort worthwhile, we'll take all comers. We'll take any design that has a probability of working and get it fabricated for you to prove to yourself and to the rest of the group that this technology is real. And this applies to the people visiting from Versatech and Shugart as well. We intend to support your activities in the same way. And if you have specific interest in doing a project, that's highly encouraged. And if there are other people at your organizations which you feel ought to be involved in this area, we can make videotapes of this lecture series available. We can invite them over for discussions and so forth. And we really want them to be participating in this activity as well. And specifically this week, we have set aside office space and alto time and so forth in hopes that you will stick around and interact with the rest of the people in the class, and not just go back to your respective organizations and get involved in the standard work for the week. And so we have space for you, and really highly encourage you to stay around and make use of the people and time and thinking that goes on here this week. I have a lot of information to cover today, and so some of it may seem that I'm sort of ripping through. If you have a specific question on the particular material that we're covering, please ask it. If you have a more general question that could be saved till later, I'd ask you to do that just because of the time limitations. I think perhaps some of the other days in the course will be less crowded and there'll be more time for discussion. But for now, please don't feel bad about asking questions directly related to the material, and we'll do the best we can. Just to give you, I don't know if we got the, did Barbara come in with those slides? Yeah. Sure. Just to give you an idea of what it means to do a design in a fairly short period, and what kinds of designs can be done, and what the chip looks like when you actually fabricate such things. We have a couple of slides of some what we call multi-project chips, which we have done here at Xerox, and a chip of some designs which were done at MIT by the students in Lynn's class. This is a slide. Does it have one more thing of brightness? Is it all the way up? This is a slide showing about 8 or 10 chips which were designed by people. Could you focus a little bit better? It's the top knob. Over. No. Okay, right there. These are some chips that were designed, several of them by students last summer who had never done any integrated circuit design in the past either. For example, this chip over here is a 16-bit error correction chip, generates Hamming codes and corrects data read back from a memory, for example, that has the Hamming code bits associated with it. And it was designed by somebody who had never designed a circuit before, and it works. And this is a chip that Dick Lyon did, and he'll be talking about that much more later in the course. And there are various other projects which were done. This one up here was done by Bob St. John, who's in the front row here. I don't know what he's doing here. If he can design that, he was working down at ADL at the time. Now he's at Versatech. Another project by a student who hadn't done design before. Could you or get the next slide? You'll be hearing a lot more about this chip on Friday when Lynn Conway describes the activities at MIT in the last semester. But here are about 20 different designs which were done by students in her course over a period of about 6 weeks using a much more primitive design language than is available to us here. And the reports are that at least 5 of those work, and maybe more of them. Some of them haven't been tested yet, but at least 5 of them work. And they were all done by students, hand coding in a fairly primitive but quite usable way. The chips were put together here and then fabricated at a local facility. Okay, you can turn that off. So that's sort of the end product, or the diploma, or the sort of the end thing of what this class is to wind up with. And we'd like each of you to contribute a project similar to, in size perhaps, to the ones that you saw there. And in fact, we've already decided on a cutoff date. April 20th is a magic day. 5 days after taxes, we want your designs done. And we'll establish a directory, and you ship them to the directory. And after that, all the magic happens behind the scenes, and you will get chips back in perhaps 4 to 6 weeks. The magic that happens behind the scenes will not be quite automatic, unfortunately, but we're working on that. For this particular project and the ones we've done in the past, we hand assemble them into one large super chip and then carry it through the various mask making and chip fabrication procedures and bring the wafers back, get them dice bonded, and then we'll present a packaged chip to you, and then it'll be up to you to test them. We will not test them for you. And so you have to design them so they're testable, and hopefully so they'll work. But April 20th is a magic date, and so start your project planning now. This is not too early. Christmas is only a short time away. And in fact, you might even want to start working on some trial pieces of the design during the class sessions, or during the homework sessions, hopefully not during the class. Okay, I just want to put up, starting to get into the more of the meat of the matter, hopefully. What are the things that we focus on in terms of doing integrated circuit design, which makes our area of focus a little bit different than that used by Intel or somebody else? And number one, we don't have a lot of people to sit there and hack about for days and days and days, making a circuit absolutely as small as possible. And so one of the things which we strive for is to develop regular structures. And this has a couple of advantages. Number one, it's a whole lot easier to design. In terms of if you're designing random logic, rather than packing together a bunch of arbitrary gates, you can make use of some regular structures which just make the design a lot easier. They make the checking of the circuit a lot easier, and they leave open the possibility of generating some of those lower level regularized structures automatically from some higher level description, which we'll be talking about a little bit later. Number two, we really put a much reduced emphasis on absolute circuit compactness. Now, minimizing the size of the circuit is important. I don't mean to say that it is not important, but as you all will appreciate from whatever design activities that you're most familiar with, getting the last 10% out of a design usually takes 50% of the time. And so when it comes down to getting that last 10% out of the area of your integrated circuit, stop. You're far enough. And especially in the type of environment that we work in at PARC, where we may only build a few hundred of something, this is especially true. And even the semiconductor companies such as Intel and so forth are beginning to realize the folly of getting the last 1 or 2% out of many of their designs, and are moving towards this use of more regularized structures, which are more easily checked, easier designed, easier to verify, and so forth. And the third, and perhaps one of the most important things, is to link up the system design with some knowledge of how the layout's going to go, of how, when you actually implement the thing, what's it going to look like. Much of the design that is done these days is done with very little thought of how the eventual circuit is going to lay out. And we found it just an extremely powerful concept to be able to have in mind the layout, in fact, use the layout in our system design thinking to actually make the circuit perhaps more compact than you might have by optimizing it at a different level. And one of the important things is this reduces the communications path length, and thus increases the speed of the circuit, and probably reduces the area of the circuit associated with just busing of signals. And so these are three of the most important factors that make up what we call the structured design methodology. and all of them will become a lot more clear as we go on. Okay, I think I'm just going to skip the next slide and move on to the next one. This is just a copy of the outline that you had before, and it's not all that important that you read everything on it. I just want to point out a few major points. We've been talking about the introduction and some of the goals of the course strategy, and now we're going to just discuss the outline a little bit. I'm going to be talking about some basic characteristics of nMOS transistors today, so that you'll have a basic mental model, not an equations model, if you will, but just a basic mental model of the nMOS transistors, so that you'll be able to manipulate the designs that we're asking you to do on the homework, for instance, tonight and later in the week, so that you can manipulate these structures with a fair amount of ease. As you do this manipulation, you don't want to always think about the equations that generate or that describe the exact performance of this device, but you need some basic, simple model of how these things operate, so that you can decide which particular construct of devices makes a workable, interesting structure, and which structures are not interesting. So I'll just be getting into those simple models in just a few minutes. Then Dick Lyon is going to be talking about using some of those the basic elements, the nMOS transistor, in building up some simple digital building blocks, some registers, shift registers, pass transistor, steering logic, and so forth, that will give you some glimmer of how you build up digital systems out of these very simple building blocks. On the second day, we're going to get into the same sort of thing in much more detail, giving you examples of a wide variety of digital systems building blocks, many of which you're familiar with in current technologies, and we'll just give you a view of how they are implemented in the IC technology business. Okay, the third day, we're going to become a little more or process specific. The first day, the designs you could apply to a variety of nMOS type of processes. On the third day, we're going to talk about how you actually turn these designs that you've been doing into something that can really be called an integrated circuit. And to do that, we're going to have to talk a little bit about the fabrication process. We're going to talk a little bit about the layout process, how you go from a basic design to an actual layout that can be fabricated, and then talk about what I call real transistors. In other words, you'll be able to, in the first couple of days, design things which work, but you won't know how fast they work. And so on the third day, we're going to tell you the basic techniques for understanding how to determine, after you know the thing basically works, how fast will it operate, and what sort of margins does it have, and that sort of thing. The fourth day, we're going to give you a systems eye view of how you go about designing integrated circuits, and using a couple of examples that Dick and I have done in past systems designs, and give you an idea of the trade-offs, how you approach the problem, what things you do first, what things you ignore till later, and that sort of thing. And also, I'll have a little bit to say about what the future possibilities are as far as scaling these things, this sort of factor of 500 that I was talking about, and where those numbers come from. On the fifth day, we have a grab bag of things. Tell you a little bit about the considerations you'll have to take for testing, a little bit about the alternate design methodologies. And then Lynn Conway is going to spend about half the day summarizing what the course has been about and describing to you the really exciting experience which she had with a similar course back at MIT, the kinds of projects which the students were able to do back there, and give you some basic feeling for the accomplishments that can come out of a short course such as this. And then last but not least is we don't mean to end at the end of this class. As I said, you're going to be working on projects after the class, and there'll be more to learn about nMOS design than what we can teach you in 5 days. And so we started to set up an advanced seminar series in integrated circuit design, and we'll have mainly people from the outside sharing with you insights and ideas that they have come across over their years in working in the field. And I hope also to get chip design examples from the class. People who have taken the class and are working on projects, come and share those designs with the rest of the people. Tell us what's going on, what the problems you're having, and let everybody learn from the experiences that you're having. Questions? Nothing to ask questions about yet. Thirsty. Okay. Now that we know that we're going to be designing circuits, what are the types of circuits that we're going to be designing? Number one, we're not going to teach you much at all about designing analog integrated circuits. We are going to be talking strictly about synchronous digital systems, and specifically what can nicely be described as a finite state machine controlling perhaps a register-to-register transfer path. You have some microcontroller machine here controlling some data path, which may be an ALU structure or various other variety of other structures or stages of ALUs or a variety of things, actually. And that's really what we want to find out from you people, or what are the interesting things that one can design with this technology. And looking at these data paths, they're really made up of just two basic kinds of things. Number one, you have registers in which to store data at various steps of the process. And number two, you have a block of logic which will allow you to transform that data from one form to another. And that transformation may be strictly a set of wires which carry the data from here to here, or it may be an ALU which adds together the values that may be present in registers here and transfers the value here. Or they may be merely crossed wires, which will allow you to shift or rotate that data, for example. As far as what this thing is up here, well, this is just more registers and combinatorial logic, perhaps, but with some feedback paths, which allows you to generate an output state which is dependent on the current state as well as perhaps some new inputs. And this is the standard finite state machine controller, which I'm sure that most of you are familiar with digital systems are familiar with. And so in the course, we're going to talk about really just two things. We're going to talk about how do you build registers and how you build combinatorial logic and how you put those things together into interesting structures. And as in making that design process predictable and regular and so forth, one of the things which is very important is to adopt a consistent clocking scheme so that everything is clocked in a synchronous, consistent way, and you don't have problems with races and that sort of thing. And so the kind of clocking system that we're going to be talking about is a two-phase non-overlap clock system which has signals which look like this. You have two clocks which are going at the same frequency. They have the same period, where this period equals this period, but they are never active at the same time. In other words, they're non-overlapping. And that's critically important to the proper operation of the circuit. And most all of the structures which you see Dick and I will be talking about over the next few days, which involve clocks, will be using clocks of this nature. Okay, now that we know what we're going to be building, the question is what are we going to be using to build it, and why? Well, we're going to be talking about the nMOS technology, which is one of a variety of integrated circuit technologies which is available to us today. And the reason we use nMOS is there are actually several good reasons. Number one, it's the most common LSI technology available today. You can go out to almost any fabrication house, and they have an nMOS process which is reasonably the same as some other nMOS house. And if you adopt a set of rules appropriately, you can actually get circuits fabricated at a wide variety of places. Number two, it's a high-performance technology. It's one of the highest performance technologies available to us today. It's a high-density process, and it has a really vital future in terms of its ability to increase the speed of the process as well as the density of the process. It's a lot easier to design than bipolar integrated circuits. There are less circuit tricks and circuit intricacies to worry about, and you can treat the system in a much more higher level way than you would be capable of perhaps when designing bipolar circuits. In addition, it's fortunate that the particular designs which we'll be talking about today are transferable to at least some other MOS technologies, and specifically CMOS, for example, which might be a thing of interest to some of us in the future. Okay, let's get into the actual devices. What is necessary to know about the devices? What are some simple mental models of those devices that will allow you to manipulate them easily when you're doing your designs? And I'm going to sort of start making a catalog of different representations and models and so forth up here, so that in the end you can sort of compare them and see how they relate to each other. The first thing I'm going to be drawing is just the simple MOSFET, which has a circuit symbol like this one. There's one drawn on the board here, and it has three terminals on it. It has the gate, and has the drain and the source. And the gate, if we look at the simplest of all models, is merely a control element for a switch which can connect the drain and the source regions. This is a voltage-controlled switch. When the voltage V sub GS is more positive than some threshold voltage, which is defined by the process in which the circuit is fabricated, when VGS is greater than the threshold, the switch is closed. And when the voltage is less than the threshold voltage, the switch is open. And so this actually is a sufficient model, I think, for doing a good part of the homework assignment tonight. You don't have to think about resistances, capacitances, or anything. Just think about switches. And that gets you an amazing distance in this world, as a matter of fact. Okay. If you look at the transfer characteristics of this device, in terms of what the input voltage looks like as a function of the output voltage, let me just put that over here. If you plot V in here and V out here, over some range from 0 to some V threshold, the output is actually well, let me see. Let me forget that for a moment. And then we'll come back to that in a minute. Got a little bit ahead of myself. Okay, so that's the basic simple model, and let me just put that model up right next to it. We've got a switch like that. This is the model. This is the circuit. Okay, now let's develop a little more complicated model, which may be helpful in some of the work tonight, but will become more into play in some of the later work, and actually will be useful for understanding some things that Dick Lyon is going to be talking about today. And this MOS transistor is really not a perfect switch. It's the drain region, instead of having zero resistance, or the drain source connection, instead of having zero resistance when it's on, really is a resistor and has a variable resistance depending on how much the gate voltage is above threshold. And it also has another interesting characteristic in that the gate is really isolated by a very strong insulator, very good insulator, from the drain and the source regions, and forms a capacitor between it and the source, at least you can think of it that way. And on that capacitor you can store charge. And so there are two interesting things to learn from this model. Number one, there's a finite resistance in the channel when the thing is turned on. And number two, there's a place to store charge, at least temporarily, on the gate of this device if you can isolate the other side of it, because this side of it is already isolated. And if you can find some way of dumping charge onto it and then disconnecting it from the thing that dumped the charge, you can actually maintain a voltage there when it's not connected to any other circuit element. As far as what the characteristics of this device look like, instead of being an ideal switch, which has a characteristic which would look like come to here, the threshold voltage, and then have zero resistance, it really turns on a little bit sloppily right around threshold, but then has a resistance. Here I'm actually plotting conductance, or 1 over resistance. A conductance which increases rapidly with the voltage of the gate source above the threshold voltage. And so the higher you go above the threshold voltage, the lower the resistance, or the higher the conductance through this channel. Okay, so because it has this linear characteristic, it can be useful as a logic element. But unfortunately, this does not tell the whole story. I'm going to now describe, these are sort of the two terminal characteristics of this thing. What does the drain source look like as a function of various gate source voltages? I want to draw another picture of the device which will be useful to you in understanding the transfer characteristics of some devices which, or some logic elements we'll be talking about in the future. In this diagram, I'm going to plot the drain source voltage versus the current, and I'm going to develop the drain source current. And I'm going to develop a family of curves at different threshold voltages. In other words, I'm going to pick different points along this curve, different values of conductance, and plot what the drain source voltage relationship is for those different values. The model here that I've described here works fine as long as the drain voltage is relatively low, or the drain source voltage is relatively low. And we'll see what relatively low means in a little bit. And so in this region down here where the drain source voltage is low, you have a family of curves where the current grows as some function of the voltage, and the slope is dependent on the value of the conductance at the particular value of V sub g that you've chosen. So as we choose values of V sub g which correspond to higher conductance, we get curves which have a greater slope in this part of the characteristic curve. Now, unfortunately or fortunately, the things just don't go on forever that way. And what we find is that out here where the drain source voltage is significant in comparison to the gate voltage, that these curves actually start to flatten out, and that the device starts to look more like a current source in this region out here. Current source is merely a device which, when you apply voltage to it, maintains a constant value of I through it. So no matter what voltage you put on this device, in other words, what voltage you place at this point, the same amount of current is going to flow through there for a given gate voltage. And so, since all things must be continuous in some respects here, we've got to find a family of curves that connect those together. And you wind up with two interesting regions. Number one, a region down here where the thing looks resistive, and a region up here where the device is in what's called saturation. In other words, the value of the current is saturated, and it starts to look more like a current source. And these are the characteristic curves which you'll see displayed in any book on nMOS circuit design. They're in Lynn's book and so forth. And the important thing to realize is there are two important regions here: a resistive region and a saturation region where the device looks like a current source. Looking at that in a little more detail, this is just copied out of the book. there's a third area which is described here, not only the resistive region and saturation region, but the cutoff region, the area where the gate source voltage is so low that this switch or resistance, the switch is open and the resistance is so high that effectively no drain current flows at all.
Doug,
Yeah.
a very small nit might get cleared up. 2 slides back, where you showed the basic MOSFET, the voltages all were plus to minus from drain to source, and also VGD and VGS. In the same picture in the book, VGD is considered to have opposite polarity, and that affects how you interpret the figure 9A that you just shown. So, which convention are we using?
You should switch the plus and minus on VGD on that slide.
Okay, that would control
this
the text.
Oh, this one here, you mean?
Yeah.
Plus or minus.
I don't know what difference it makes except
Well,
for how you read and write.
Yeah, they'll. Okay. Yeah, I should do it that way because it's the gate drain voltage is the way it's. Okay, that was wrong. Thank you. Okay, and again, you see this fairly linear region here where you're in the resistive range of the device, and a fairly flat region here where you're in the saturated or current source region for the device. Now that we've got a basic device, what we'd really like to do is build some logic circuits out of it. And going back to the simpler model to give you an idea of the sorts of things you might want to build, probably the simplest device is an inverter. And we can build an inverter by just putting some resistance up here as a load device, connecting this to some positive supply voltage, which we'll call VDD, and we'll apply some input voltage here and expect to get some output voltage here. Looking at the model for this device, you have just the resistor, which now we're going to model this thing as a switch again, just to make it simple in the beginning, and a ground. And you can see that, and this is a voltage-controlled switch, remember, by V in, and you have V out. And you can see that, now getting to the transfer characteristics, if you plot V in versus V out, as long as the input voltage is low enough, the output voltage will be pulled all the way up to VDD through this resistor, and it will sit at some value up here, very close to VDD, if not at VDD, until you reach the threshold, at which time the output will immediately drop because it's shorted to ground to 0. And those are some nice ideal switching characteristics, and wouldn't it be nice if we do that? Well, it's not really quite that good because, as we've discovered, this device here is really not modeled perhaps sufficiently well for all cases by a switch, but rather by a resistor. I'll draw that down here, I guess. A voltage-controlled resistor at that. Again, we'll put a ground thing at a VDD connection, your output voltage, and input voltage. And looking at what the characteristics for that device would be, we have, as long as you've chosen a value of R which is appropriate, and the appropriate value of R is actually shown in the next slide. RL should be, this is RL here. RL should be much greater than the off resistance of the inverter, and should be much RL should be much less than the off resistance and much greater than the on resistance of this particular nMOS transistor. That's not too hard to do as long as you're dealing with discrete components, but we'll talk a little bit about that in a minute. Assume that you've got some resistor that will do this. The transfer characteristics, instead of having this ideal set of characteristics, would start at some value, depending on this resistive dividing ratio, less than VDD, would have a finite slope, depending on what the value of the RL was, and would not come all the way down to 0 because of the voltage drop across this resistor when it's on. And so somewhere in here, you would have a V threshold, and you start to wind up with some characteristics for the inverter which are more appropriate or more typical of what physically happens in such a circuit. Let me define some other representations here. One of the big things, or perhaps confusing things about this course, is it will be forever switching from one representation for a circuit or design to another. And sometimes we'll be using logic representations, sometimes we'll be using circuit representations, sometimes we'll be using what we call stick diagram representations, which we'll get into in a minute. And all of them have their particular place depending on what the particular idea or thought that you're trying to get across at that time. For this discussion, it's appropriate at this point to be talking at this level. For a later discussion about system architecture or building up shift registers or something, a representation of the inverter as a simple logic inverter is the most appropriate thing. And so let me just draw that there. Okay, so we're getting closer to what we actually use in physical circuits to make an inverter, but we aren't quite there. But before going into what it actually is, let's think about this model of a voltage-controlled resistor and think about what other basic logic elements we could build out of that simple structure. You can see that if you chose, if you drew a circuit like this with an RL and had one of these voltage-controlled resistors in series with another one, you could have a NAND function where this is the output, and if both A and B were above threshold, then you can see that there would be a low resistance path to ground and the output would go low. And the logic representation of this circuit is then the standard NAND gate representation. The other interesting type of gate structure that you can build easily with this is a NOR gate, and there you just put these two voltage-controlled elements in parallel with each other. And this is the output. This is A. This is B. And the logic representation for this is the standard NOR gate representation, where if either A or B is high, then there is a path for current to flow to ground, and the output will go low. These are all connected to VDD. This is RL. Okay, so we're building up a family of interesting logic circuits and representations. However, life is not quite as easy as that, because as the last line says, it's really hard to make resistors in nMOS. So this is all a fine model, but what are we going to do for RL? And you think, well, we just got finished saying that a transistor is, or that an nMOS transistor is really just a voltage-controlled resistor. And so if we could just make it some sort of pseudo-fixed value of resistance somehow, we could have a load device perhaps, and it might even have the right value if we're fortunate. And so the technologies people went to work and came up with a device which is called a depletion load device. That's as contrasted with the enhancement mode device, which is here. These are all enhancement mode transistors. In other words, you enhance the gate, you turn it on more positive to turn the thing on. Depletion mode transistor is already on at 0 gate voltage. And what that means in terms of our old diagram is that, going back to the basic resistance thing here, or the basic conductance of the channel, what we find is that this a depletion mode transistor, or what we're probably more commonly call the yellow transistor, because for reasons you'll understand later, the brown pencil that you have is for yellow transistors. And we'll be using a variety of colors other than yellow to describe it. We'll use the name yellow to describe it anyway. Sorry about that. It's merely the same sort of transistor, but its threshold voltage has been moved to the negative voltage regime so that it turns on down here someplace. Its threshold voltage is in this area. And at zero gate voltage, or zero gate to source voltage, it already has some reasonable value of conductance. And so what would such a device look like? Well, in a circuit representation, it would look like your basic transistor with zero gate voltage. And the way you guarantee zero gate voltage is you connect the gate to the source. And literally and every other way, you just physically connect the two together. And you get a device which has a conductance defined by wherever this curve crosses this value here. And you choose the thresholds in an appropriate way to make that conductance value the right thing to use as a load device. And so what we do to actually fabricate these various circuits is to replace this load device with a depletion mode transistor. We just put that in the place. In fact, this one I'll just erase. And